In Ukrainian prisons, they teach you calculus too.
That's all they
They
do.
teach you
That's all they do. They're
That's only way you
like, this
live.
is a form of torture. Welcome to our prison.
Either
We're
this
going to
infinite-
teach you
you
calc
determine
too.
if this infinite series converges or diverges or else.
Do it! I've got your toenails.
Right? All right, so let's go ahead and finish up 10.3. The last class, so last Thursday, we had just sort of showed that you are going to find in nature all sorts of these geometric series, progressions that you can use to, in this example, find the area of a parabola using this method of exhaustion.
I heard the Zambo.
The Zambo, you hear this one?
Yeah.
A lot of these finding areas of shapes things can be found by using geometric shapes that sort of exhaust the whole area. And so it's ideal if that exhaustion happens to be in the form of a geometric series, because then you can apply our simple formula for the sum of a geometric series. Sum of a geometric series, A divided by 1 minus R. Nice simple formula for that sum. So what we want to do next is take a look at some properties of all series, not just geometric.
Properties of all convergent series or all series in general?
Properties of all convergent series. So these again are super intuitive. It's kind of like the properties of sequences. If you have two sequences that converge and you add them, that new combo sequence converges to the sum of the original two convergent series or sequences. Same with series. If we have if we have a series that converges, the A sub k series converges, and you multiply every term by a constant, you can factor the constant out. So that's sort of the standard factor constant out of a limit, a derivative, an integral, now a series. Constant can always be factored out. And if we have a series that diverges, there is no constant that you could multiply through by that would then change the series to converge. So if you have a divergent series and you multiply by any constant you can imagine other than 0, then it's still going to diverge. So you're still going to have divergent. And then if we have two series that converge, series A sub k converges to A, series B sub k converges to B, exactly what we think. If we add the two series together or subtract the two series, we are going to get, the sum is going to converge to A plus B, the difference is going to converge to A minus B. Super intuitive things. If you have one series that diverges and one series that converges, doesn't matter whether you add them or subtract them, you are going to get divergence. So if you have two series and one diverges, that divergent one is going to dominate. You can't take a convergent series and a divergent series and add the terms together and get a convergent situation. So diverge is going to dominate if you've got one or the other.
And what is a convergent minus a divergent?
Divergent. If you take a divergent and a convergent and you try to add them or subtract them, it's going to diverge.
So it'll just be go down to negative.
It could be to negative infinity or positive infinity. Diverge means one or the other or oscillate.
Okay.
So it just means it doesn't converge. So there's no way to make a divergent series converge by adding stuff or multiplying by a constant. If it's divergent, it's going to stay divergent. So then we have this thing here. If m is a positive integer, what they're getting you to think about here is the complete series and the tail of the series. So if it starts at capital M and capital M is further down the road, we have our a sub 1, a sub 2, etc. If we go all the way out to a sub m, that's the tail of the series. And all they're saying is that the tail of the series has to do the same thing that the entire series does. In other words, if you chop off a finite number of leading terms, it has nothing to do with convergence or divergence. If you throw away the first million terms in your series, the tail is still going to either converge or diverge. It's going to do the same thing that the whole series did.
But we'll go to a different number.
But it will go to a different number. Yeah, if we're dealing with a series and you chop off those leading terms, it doesn't change whether the series converges or diverges, but it would change what it converges to if they're converging. You know, because those first terms are the bigger terms, right? Because the terms have to go to 0 if you're going to get convergence. If you start adding terms together and their terms aren't going to 0, then you're going to get divergence. The terms have to be going to 0. That's a necessary condition. And so that's just kind of the summary here. The leading terms are those with small index values. The tail, you know, it's the end of the series. They have large and increasing index values. The convergence or divergence depends on the tail. You know, what it converges to depends more on the leading terms, because those tail terms are going to 0. So we have our one of our first interesting kind of fractal things, the Koch snowflake. And as you go on in math, there's going to be all these kind of interesting examples. This is an example of a region. So it's in the xy plane. It's a region. And it will have finite area, yet infinite perimeter. So the perimeter around this is going to be infinite, but you can just look at it and realize that the area has to be finite. You can draw a circle around it. If you can draw a circle around it, the area's got to be finite. And so this, I put together kind of, I hope, an intuitive approach to finding both the area and the perimeter by breaking things into the number of segments per side. So here we have 1 segment per side. Here we have 4 segments per side. And then here we're going to have 16 segments per side. And then finding the length. If we start with 1, 1, 1, the Koch snowflake is found by removing the mid-third of each side and replacing it with this equilateral triangle right there. And so the side length here is 1. The side length here is going to be 1/3. Each of these little segments is 1/3 of what the original was. So here we're going to have 4/3 as the length of one side. And then we have 3 sides, so 4/3 times 3 would give us the perimeter. So this gives you kind of, I think, a pretty easy way to sort of figure out what the perimeter and what the area is. So the area calculation, if you look at it carefully, you're going to end up with the area of the original triangle plus an infinite series. And that infinite series, if you do a little bit of arithmetic, you're going to get down to right here, where that is geometric. Geometric is that exponential summand. You have a constant raised to the k. Right? That's exponential, that's geometric. That 3/4 is a constant, so it factors out the front to the front. And then right here is our a over 1 minus r. This geometric series, it starts at 1, so the a value is 4/9. The r value is also 4/9. So we get that the area of the Koch snowflake is that when we start with 1, 1, 1. So the area of that snowflake is going to be 2√3/5. The perimeter is pretty easy to see is going to be infinite. So if we look at our perimeter calculation here, we're taking the 3 number of sides, number of big sides, 3 big sides, and then we have the segment length is L and the number of segments per side, blah, 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 blah. We get over here. There's our general formula for the perimeter. And that is an exponential expression with base bigger than 1. If base is bigger than 1 and you do repeated multiplication, it goes to infinity. 4/3 times itself gets bigger. So as we go through infinite series, there's always going to be these interesting examples. And there's analogs in 3-dimensional space also. There's something called the Sierpinski sponge, which will have infinite surface area but finite volume. Same kind of idea. You've got this fractal nature. I think this fractal stuff is interesting. If you are just looking for light reading over the summer, there's a great book called Chaos. And this stuff was just developed in the 70s, not that long ago. And it just became more sort of concrete 30 years ago, 40 years ago, not too long ago.
Fractals used in German U subs
You know, fractals are used
for decoding.
all over the place. Like the one main application that we've seen in our lifetime is cell phone antennas. Like, you know, the original phones had these antennas, and then if you read that book Chaos Theory, they'll talk, I believe that this story is in there, you know, figuring out that you can create a fractal antenna, you know, with all these little, you know, sort of like that, and it can receive signals way better than just like a, you know, like one, you know, like thing that you pull out of your, like the old phones had just a single antenna, or the cars had those single antennas.
Wait, the 70s were like 50 years ago, not 30 or 40.
Well, the first book came out in the 70s, but a lot of the research wasn't sort of solidified until 70s, 80s, 90s.
We're actually closer to the 70s and the 21st.
You're so young. But the fractal thing is pretty cool, you know, so originally we sort of didn't think about dimension as being a real number, a positive real. We thought of dimension as being integer valued, you know, 1 dimension, 2 dimensions, 3 dimensions. And then with the whole study of chaos theory, of fractal studies, study of fractals, they started doing the measurement of the coast, and it starts to become intuitive. If you're measuring the coast and you're using segments that are 1 mile long, you're going to get one measurement for the East Coast. If you use a yardstick, you're going to get something that is going to have a different value.
Is that the one?
That guy, that book is really good too. That guy, Stephen Strogatz, he's like the man in terms of taking complex math and delivering it to the masses. He used to write a column in the New York Times that was the math column for like 20 years. And yeah, so Strogatz, anything that he writes is really, really good. The one that I'm talking about is written by James Gleick.
Yeah, chaos making new science.
This one. Looks better.
Is that James Gleick? Yeah, that one.
Ooh.
Yeah, that was sort of
Well,
like
it's cheaper too than the other one, so we'll take it.
yeah, that one is really sort of the beginning of the chaos study. But it's interesting. Then you use, you know, like if you use your resolution down to an inch, you're going to get more. And so they came up with a concrete way to figure out, okay, the east coast of the United States has a 1.4 dimension. Like you can make it concrete. You can mathematically define partial dimensions, which is fascinating. And of course, it's all over nature, of course. Okay, so let's go to 10.4. We are now moving into the non-S sub n series. So with geometric and telescoping, you could find S sub n. So remember that with geometric and telescoping, if you can find S sub n, if you have a formula for S sub n, if you want to know whether the series converges or diverges, all you need to do is take the limit of a sequence. And the limit of a sequence is relatively easy. You let n go to infinity and you figure out what happens. There's very few, there's not a lot of depth there. You're just taking the limit of S sub n. But again, the problem is a series other than geometric or telescoping, finding that S sub n is virtually impossible. You know, so that is what we are starting to get into with 10.4. So we're going to, the main idea in 10.4 and beyond is, okay, non-geometric, non-telescoping, what do we do? So we're starting with a theorem here. It's called the divergence test. If we have a series that converges, so series A sub k converges, then the terms must go to 0. So if series A sub k converges, then the limit of the sequence of terms must be 0. So that is our fundamental building block with series. The only way you can add up an infinite collection of numbers and get a finite answer is if you're adding progressively smaller and smaller and smaller and smaller and smaller numbers that are going to 0. And they're going to 0 fast, relatively fast. So another way to rewrite this logic here is with the contrapositive. So the contrapositive says, so if we think of this as P and Q, so if P, then Q, the contrapositive is equivalent, and the contrapositive says not Q implies not P. So if P implies Q, the contrapositive, which is logically equivalent, says not Q implies not P. In other words, if the limit of a sub k is not 0, then the series must diverge. So that's the those are two logically equivalent statements. So if the series converges, the terms go to 0. If the terms don't go to 0, the series doesn't converge. And there's a great example here that sort of gets you into the thinking here. So if I live in Paris, and we're talking about the Paris with the tower. If I live in Paris, then I live in France, necessarily, right? If I live in Paris, I live in France. The contrapositive is logically equivalent. If I don't live in France, I don't live in Paris. Paris with the tower, not Paris, Texas. So that is equivalent logically. So contrapositive is logically equivalent to the original, if P then Q. Now the converse is generally, well, you can say that the converse is not necessarily true, and it's usually false. So there are some statements for which if P implies Q, Q also will imply P. Most of the time that's not true. So for us that is not true here. The converse is not true. So the converse of this says if Q then P. So if the terms go to 0, the series converges, and we already know that's false. We've already talked about the harmonic series. So for us, the converse is false. This harmonic series, the terms are going to 0, but that series is going to diverge. The harmonic series, 1 plus a half plus a third, this diverges. This goes to infinity. So it's not enough that the terms go to 0. They have to go to 0 necessarily, but it's not sufficient. Just because they go to 0, that's not enough. They have to go to 0 fast, what we call fast. So if we look at the thing like 1 over n squared, so this, they are going to 0 fast enough. So this one is going to be finite. This one is going to converge. There's lots of ways to say this. It's finite, it converges. We can figure out what it converges to in some cases.
But importantly for us, if it doesn't, then it can't converge.
Right.
Which means that we can just check
We're
it
done.
and we're done. It
Right.
diverges because we don't have
So if the terms don't go to 0, we're done. The series has to diverge. But you cannot show that a series converges with the divergence test. The divergence test can only say, oh, it diverges, the terms aren't going to 0, it diverges. If the terms go to 0, then we say the divergence test is inconclusive. We have to do more analysis. So if the terms are going to 0, that means the series might converge, it might diverge, we have to try another test. But if the terms don't go to 0, we can definitively conclude the series diverges. So that's going to be our basic bedrock principle here. If the terms go to 0, do more analysis. If the terms don't go to 0, diverge. So that is the divergence test. It's either conclusive, that the series diverges, or it's inconclusive, which means we don't know. We have to do more analysis, which is what all the other tests are for, the more analysis part. So let's try this. So use the divergence test to determine whether the following series diverge or the test is inconclusive. It's got to be one or the other. So we start by taking the limit of a sub k. So the limit of a sub k, in this case, means the limit of k cubed divided by k cubed plus 1. And there's a couple of ways to do this. You can do the college algebra way. Powers match, limits the quotient of leading coefficients. You could do that. Or you could do the more mathy way, divide by the highest power of k here, and that sort of turns it into a limit that we can evaluate by inspection now. So now we can say that, okay, this limit is going to be 1 because we know that 1 divided by k cubed as k goes to infinity, this is going to go to 0. So the overall limit is 1. So what is our conclusion then?
Divergence.
So this implies divergence. Because that's not equal to 0. Maybe I'll put that in there too just to emphasize. So because that's not equal to 0, so this is not equal to 0, therefore diverge. So we use the little 3 dots. Are you all familiar with that? The little triangle of dots means therefore. So therefore we have divergence because the limit is not 0. So we've concluded that that series diverges. Okay, let's try this one. So same idea. We're going to take the limit of a sub k as k goes to infinity. So that's the limit of k divided by natural log of k. This is an indeterminate form. So is the one above originally, right? Both top and bottom are going to infinity, so it's indeterminate. And so we can apply L'Hopital's rule. That's another technique. We could have applied L'Hopital's rule 3 times to the top one also. That would work. Take 3 derivatives. That would work. It's more work than you want to do, though, if there's another technique. Here, though, that seems like the most logical thing to do. Take the derivative of the numerator and the derivative of the denominator. So again, our logic there is that a fraction of functions is going to approach the same thing as the fraction of derivatives. Why? Because the derivative is the best approximation. So the fraction of derivatives should go to the same thing as the fraction of functions if it's a legitimate best approximation. So this becomes the limit of k as k goes to infinity. And what is that? Infinity. That is not equal to 0. Therefore, we have divergence. So that is the divergence test. The next one, same strategy, and so this is something that when we look at a series, maybe we don't write this down, but we think it real quick. This is the first thing that should flash through our heads is, are the terms going to 0? That's the first thing, and if you look and the terms are going to 0, then you know you've got to do more work. And like in this case, I see a polynomial divided by an exponential. I know those are going to 0. Exponential grows faster than a polynomial. That could be k to the 5 million divided by 2 to the k. That will still go to 0. An exponential dominates all polynomials. So this is going to go to 0. So a lot of the math with infinite series should confirm what the logic is. Like we should be able to logically sort of think through most of these before we even do the math. And so in this case, we get the limit of a sub k. That's the limit of k squared over 2 to the k. All right, that's also indeterminate. Bless you. We have infinity over infinity again, so we can use L'Hopital. Now our intuition is because of growth rates. We know that exponentials grow faster than polynomials, so that's our intuition. But if you can do the math, you do the math. Like this next one, factorials grow much, much faster than polynomials, or exponentials even. This one we can't do the math. Here we have to apply to the growth rate concept, because we don't know how to differentiate k factorial. Bless you. So, is spring here?
Yep.
Oh boy.
It's past 21st.
It is. So we're going to take the derivative of the numerator. Now we have to remember how to differentiate an exponential with a base other than e. So the first thing is it's itself, but then what's the extra factor?
ln of 2.
ln of the base, exactly. So if it was a natural exponential, natural log of e is 1, so that factor would not contribute anything. But when the base is not e, then we have to do that extra multiplication. Okay, well, this is still an indeterminate. It's still this, still indeterminate. Still an indeterminate form. So we're going to apply L'Hopital's rule again. And here we're set now. The derivative of the numerator is 2. The derivative of the denominator, it's itself, 2 to the k. Then we have to multiply by natural log of 2 again. So we end up with natural log of 2 quantity squared. Now we can evaluate the limit. The numerator is constant. It's fixed. It's not moving. But the denominator is exploding. It's getting bigger and bigger and bigger and bigger and bigger. So the fractions are shrinking to 0. Shrinking towards 0. So this limit is 0. So what's our conclusion?
Determinant.
Yeah, it's inconclusive. Inconclusive. Right? So that is inconclusive. So if we get a 0, that means we don't know whether it converges or diverges. Now, what do you think intuitively? If we have a polynomial up top and an exponential down below, do you think this is going to converge or diverge in the big picture? Converge.
Depends though on how big the, does it?
It's not going to depend. If this is an exponential growth, and that's only a polynomial, those terms are going to go to 0 fast enough.
It will.
Yeah, they'll go to 0
What
fast
about,
enough.
what about exponential over factorial?
That'll go to 0 fast enough. So that growth rate thing will actually be sufficient in terms of deciding whether we have convergence or divergence. So the slowest thing that converges that we've really seen is 1 over k squared. Like that converges. 1 over k diverges, but 1 over k squared converges. And we did a couple of little finicky things in the middle. I think we looked at 1 over k natural log of k, and we got divergence, I believe. So we've looked at a couple of things, but in our mind, 1 over k squared, we know that's going to converge, and 1 over k is going to diverge. These terms are going to go to 0 faster than 1 over k squared. If you divide by an exponential, that's going to go to 0 even faster than 1 over k squared. And so then here, this is one where we really, we can't do the math. All we can do is use the heuristics that the factorial grows faster than a polynomial. So this is going to be, all we can say is that this limit is 0 by growth rates. And therefore, this is inconclusive here. So we have to do more. We have to use another test. The divergence test can only find divergence. And if we don't have a limit, if we don't have a limit that is not 0, then it's inconclusive. If the limit is not 0, did I say that right? If the limit is 0, the test is inconclusive. If the limit is not 0, the test is conclusive and the series diverges. So, now the harmonic series, we've talked about it going to infinity, but we haven't actually proven it. We did show that 1 over x, if we integrate it, that 1 over x diverges. If it's an improper integral that diverges. Now we want to actually come up with a mathematical reason that the harmonic series diverges. So the harmonic series diverges, even though the terms go to 0, still it diverges. So here is what S sub n looks like. Now S sub n, we cannot find a formula for that. This is not a geometric series. It's not a telescoping series. We can't find a formula for S sub n, like a closed formula that we could take the limit of. Can't do it. So here's what we are going to do. So we're going to refer back in our mind to improper integration. And remember that the area beneath a curve, you can think of it as a sum of rectangles. So let's take a look at this. So visually, here's our curve, 1 over x, and we've got our sequence of terms that are right here. And isn't it true that this height is 1 and also this area is 1? Right? We can use the area of that rectangle to visualize the value of that term. Everyone agree with this, that the height and the area are the same because the width is 1? So if the height is 1 and the width is 1, the area is 1. If the height is a half and the width is 1, the area is a half. So we can use rectangles to visualize the value of each term. Okay, so here's the first term. There's S sub 1. And then if we add the second term onto it, the sum of those two green areas, that's S sub 2. And if we go all the way down here and we sort of keep this straight and we look at this last rectangle right there, let's see. So the first rectangle, the 1 is on the left. The second rectangle, the 2 is on the left. The 3 is on the left. The n is on the left. So if we add up all those green rectangles, that's a visualization for what S sub n is. The sum of all these green rectangles is a visual for S sub n. S sub n means the sum of the first n terms. So in this case, the sum of the first n rectangles. Okay, and do you see that S sub n, we have overhang here, right? There's more green than there is under the curve. The integral of the curve is the area beneath it. And this S sub n, if we were to integrate from 1 over to n plus 1, we get the area under the black curve, right? That area right there is less than S sub n. Everyone agree with that? Can you visually see that the area under the black curve is smaller than the area of all those green rectangles? Okay, because this integral means the area beneath the curve of 1, that's a weird way to write it, but we do it all the time. Dx over x. So, let's take a look at this integral then. So this integral from 1 to n plus 1 of 1 over x. That's a definite integral. And 1 over x is defined on that interval, so it's a definite integral. That's going to be natural log of the upper limit minus natural log of the lower limit, which means the integral from 1 to n plus 1 has this value right there. So we didn't come up with an equation for S sub n, but we do know that S sub n is bigger than that. And what is true about the limit of this? It's infinite. So if we take the limit of that, the limit of ln of n plus 1, this is infinity. And S sub n is bigger than that, so it must also be infinite. So this implies that the limit of S sub n is also infinite. Therefore, the series diverges. Therefore, I just want to say diverges. Therefore, diverges. So that's our basic approach to finding the sum of a series. We're going to take the limit of S sub n if we can find it. In this case, we couldn't find S sub n, but we found an inequality that told us S sub n is bigger than something we can take the limit of. So next best thing. Any questions on that? Yeah?
It would also work to find the limit of something, find a series that is greater than S sub n and does converge. So if we had it the opposite way, if we had a convergent series and we say, well, it's less than that.
Yes, 100%. So that test is going to be called the comparison test. So we're going to have another,
Calm down.
right? We're going to have another basic principle. If you have a series that's bigger than a divergent series, it must diverge. Similarly, if you have a series smaller than a convergent series, it must converge. All right, so smaller than convergent is going to converge, bigger than divergent is going to diverge. So that's going to be another strategy that we're going to use quite a bit. Bigger than divergent diverges, smaller than convergent converges.
It's basically the squeeze there.
Yeah, it is basically the squeeze theorem. Okay, so what we just did leads us to our first real test. The divergence test is a test, but a lot of times you're just doing it in your head real quick. It's not quite as robust as some of these regular tests, which can tell both divergence and convergence. So the tests that are coming, and I forget exactly how many we have. If you look at your handouts, the tests are there, and actually I think I have them down here somewhere too, where we have all of our tests summarized. Maybe I thought I had it somewhere down there. Let's just look for a second at handouts, because it's definitely under handouts. If we look at our
Convergence test?
convergence tests.
Sure did.
Oh, I've already highlighted it. I guess I knew where we were going. So here is the list of all the tests in the order that we are doing them. So we've already done the geometric and the telescoping last week. Divergence test and integral test, so that's 4, 5, 6, 7, 8, 9, 10 total tests. So today, divergence test and the integral test. This is a nice little summary. The book has a summary too that's kind of this big table and thing, this kind of a little bit unwieldy. If you look at this, I tried to just grab the nuts and the bolts of each test. And that is enough for us. And if we think about the geometric series, the most important thing is this right here. If we have a common ratio less than 1, we have convergence for a geometric. And we're going to notice that when we get a little deeper down here, we're going to have a similar type of thing. If we have less than 1, we have convergence. Less than 1, we have convergence. So we're going to see that some of these other tests are going to act like the geometric series. But we'll get to those. And then Lincoln was talking about this idea here. Comparison, these two are comparison tests. And if we have a series that converges, if we know that B sub k series converges, then A sub k series must converge if it's smaller than it. And similarly, if the B sub k series diverges and the A sub k series is bigger than it, it's got to diverge. But we'll get to those. So this is a good sheet to start trying to read and internalize, because that summarizes all of chapter 10 right there. So that is a good handout to print out and start understanding. All right, so where are we at? Harmonic, we just did that. Okay, so integral test. So here is what the test says. We are thinking of the terms in our sequence or series, like A sub k is a sequence of terms, and when we add them together, we get the series. So you can talk about the terms of the series or the terms of the sequence, the A sub k's. Doesn't matter how you think of it. So the A sub k sequence, right there, it's a function. And we've talked about a sequence as a subset of a continuous function. So that's what we're going to visualize. So if we visualize this sequence, the A sub k sequence, as a subset of this continuous function f of x. That's what we're thinking, just like we just did with the harmonic. So if f is continuous, so f is the function, the continuous function. So if it's continuous, it's positive, meaning it's above the x-axis. So we're visualizing like 1 over x squared, 1 over x cubed, something like that. And it's decreasing. So we're imagining the ski slope, down like that. That's what we're visualizing. Continuous, positive, and decreasing. All right. For x greater than or equal to 1, our sequences start at 1 typically. And the sequence is going to be a subset of that continuous function. Then, here is the integral test. The infinite series and the improper integral do the same thing. So the improper integral is measuring the area beneath the curve, right there. The series is measuring the sum of all those rectangles. So they do the same thing. The infinite series and the improper integral do the same thing. That's what this test is all about. Either both are going to converge or both are going to diverge. So this is what we did in the last chapter, those improper integrals. They're really bedrock types of ideas for infinite series. You know, you're finding an unbounded area. You're determining whether an unbounded area is finite or infinite. It's the same idea. There's an infinite number of little rectangles in there. So here's how we prove the integral test. So here is a definite integral from 1 to n. There's the definite integral. So this is squeeze theorem. Everyone agree definite integral is just the area beneath the curve from 1 to n right there? Now we're going to look at here the leading terms from k equals 2 to k equals n. So the leading terms right here. So these terms right here are the leading terms right there. So here we're going to look at terms from 2 to n, and here we're going to look at terms from 1 to n minus 1. And what we see is that when we add up these n minus 1 terms right here, how many terms are in each of those summations? How many terms are in this one?
N minus 1.
N minus 1? Everyone agree with that? If you subtract 1 from here, you started at 1, and then you would subtract 1 from up there, so you'd have n minus 1 terms. So both of these are representing n minus 1 terms. It's just shifted 1 term. This is counting terms a sub 2 through a sub n, that's n minus 1 terms, and this is counting the terms a sub 1 through a sub n minus 1. So this one is just chopping off the first term. And whenever you do these rectangle things, remember that you can always look on either side, right? If your height is 1, if you wanted to, you could visualize it, this way if it's more useful. You can decide whether you want this rectangle here to be visualized here or over here, right? There's a way to do it under the curve or a way to do it where it's over the curve. And so that's what they're doing with this. They're saying, okay, we're going to look at these n minus 1 terms, and we're going to position these rectangles. We're not going to visualize them like that. We're going to visualize them under the curve. So those n minus 1 rectangles right there are under the curve. And if those are under the curve, that partial sum, and we chopped off the first term, that's okay. This is still n minus 1 terms right there. And that partial sum is going to be under the curve. Here, if we include that first one, and we instead visualize it as over the curve, then there are n minus 1 rectangles. And we can see visually that that area is more than the area of these beige ones and less than the area of those green ones. Okay, so now we have a squeeze thing. This area is in between both of those. If we take the limit of all these things, if this limit in here is finite, that improper integral is finite, then both of these are going to be finite. If that improper integral is infinite, then both of those are going to go to infinity, and the series would have to diverge. Okay. Now, do you agree that these two series do the same thing? Like if we let, bless you, if we let n go to infinity, the only difference between the series on the left and the series on the right is that the one on the left, we tossed out the first term. Right? This one starts at 2, this one starts at 1. Either they're going to converge or diverge. They have to do the same thing. And so if that integral in the middle converges, then both of those are converging. If that integral in the middle diverges, then both of those are diverging. Okay, so that is the integral test. When do you use the integral test? Well, if the divergence test is inconclusive, you don't have a geometric series, and you don't have a telescoping series. Like if you see a series and it's geometric, then you're going to go the geometric route. If you see a series and it's telescoping, you're going to go the telescoping. If you try the divergence test and it's inconclusive, then you have to pick another test. The main thing with the integral test is that you've got to be able to do the integral. So if you look at your summand and it's not integrable, if you don't know how to integrate it, if it's a k factorial, for example, then the integral test makes no sense to choose. The only reason you would ever decide on the integral test is if you can integrate the summand. So let's look at this. So let's think about the divergence test because that's always a good starting step. Do these terms go to 0 or not go to 0?
They go to 0.
They go to 0. That means the divergence test is inconclusive. We have to do more work. We can integrate that. That's just a power of x in the denominator. We know how to integrate powers of x. So what we're going to do is consider the integral from 1 to infinity, and we're going to turn the k's to x's so that it's more palatable. And we can put the dx in the numerator, even though it feels like it should be off to the side. So there's an improper integral. That was the last chapter. So if we can show that this improper integral converges, then we have shown that the series converges. We have no idea what the series converges to, but we know that it converges. So the first thing, as you learned from exam 2, whenever we have an improper integral, we have to take a limit. So we take a limit by going from 1 to b, and we let b go to infinity, and we know that we're going to get convergence here, right? We've already shown that 1 over x squared converges. 1 over x squared has an area that's finite. Now we just have to go through the math. So we're going to pull the denominator up to the numerator. So we have that. Now we have standard power rule set up. So this is going to be the limit as b goes to infinity. We add 1 to the exponent. Add 1 to the exponent. We divide by the new exponent. And then what about reverse chain rule?
Divide by what's divide by the integral?
Divide by the derivative of the inside, which is 2. So reverse chain rule, we divide by the derivative of what's in the parentheses in combination with the power rule. So the power rule says add 1 to the exponent, divide by the new exponent, but then reverse chain rule says also divide by the derivative of whatever's in the parentheses. All right, so then let's rewrite this in a more easily analyzed form. Let's get rid of the negative exponents. So lots of you take limits incorrectly on the exam when you left the exponent as negative. Oh, and I forgot what should be here. This is a definite integral, right?
Evaluated from 1 to b.
The evaluation from 1 to b. So then we have the evaluation from 1 to b right there. All right. So then we end up with, let's see. We can pull the negative 1/2 all the way to the front if we want. You don't have to, but I'm going to pull it all the way out to the front. And then we're going to take the limit of whatever is left evaluated at b and evaluated at 1 and take the difference. So we're going to have 1 divided by 2b plus 4 minus, when we plug in a 1, we get a 6th. So there's our limit. And this is as b is going to infinity. And what is true about this fraction right there? Where's that fraction going to as b goes to infinity? 0. That's going to go to 0. So that will go to 0. So that tells us that our overall limit is negative 1/2 multiplied by negative 1/6, which is equal to 1/12. So 1/12 is a finite number. That means the improper integral converges to 1/12. And if the improper integral converges, then the infinite series converges. So therefore, we can say both converge. So both converge, and by that we mean the improper integral and the series. So both converge. So the improper integral converges to 1/12. That's the area beneath the curve. And the series probably converges to something not dissimilar from 1/12, probably pretty close, but definitely not equal to it in most cases.
And in this case, it's a bit larger than 1/12, right? Because this is
Yes.
the case where k is 1, right?
Right.
4, yeah.
Yeah, so it's gonna overhang a little bit more like that one.
So it's not a bit taller than, or larger than 1.
So you can go into Desmos. Desmos has series. You know, you could, if you did in Desmos, if you went from 1 to 1,000, we'd get a pretty good sense of what the value of that series is. Okay, so that's a 1 over x squared thing. We knew it was going to converge. We should always know what's going to happen if we're dealing with denominators that are polynomials. So now here they're fiddling, they're messing with us a little bit. So we showed that if we had 1 over k times natural log of k, that we still had divergence. So they're going to go through this little kind of ratcheting thing. So let's think in our mind for a minute. So natural log of k is bigger than 1 as soon as you get out a couple of terms. Natural log of k is bigger than 1. When you're thinking of the natural log function, you should be thinking of the bird wing type thing. It looks like that. Right? If you get out a couple terms, it's more than 1. So in other words, k multiplied by natural log of k is bigger than k. All right, so we're sort of looking at how quickly the denominator is increasing. So 1 over k diverged, 1 over k converged, 1 over k natural log of k is somewhere in the middle, and we showed last week that that actually diverged. So now they're bumping the denominator up a little bit more. So they have k in the bottom, multiply by natural log of k to increase it a little bit, multiply by natural log of k again to increase it a little bit more. So now this one is in between a k ln k in the bottom and a k squared and a k on the other side. So let's see if this one converges or diverges. Ew. So again, if we think in our minds about the divergence test, it's inconclusive. Denominator is going to infinity, fractions are going to 0, divergence test tells us nothing. It's inconclusive. But we know how to integrate this. This is just a substitution. So we're going to do an integral. We're going to look at the integral from 2 to infinity, and we're going to put x's in here. You don't have to, but x generally in math means a continuous variable. K and n usually mean discrete. All right, so whenever we have an improper integral, we need to introduce a limit. And so these limits, these improper integrals, when we use the integral test, it's always going to be b going to infinity. We're not talking about vertical tails. All right, so we're there. And now we have to use an integration technique called substitution, the primary technique. What do you think you want to let u equal? natural log of x. And that's a great choice because its derivative is present. U substitution only works if the u that you pick has a derivative that's present. What is the derivative of natural log of x? So we get du equals 1 over x dx, dx over x. And that is present right here. There's dx over x right there. So that's great. That is what makes substitution work, when the derivative of your u is present. So let's see. All right, we have the integral from 2 to b. Oh, those are x limits. Let's put in some placeholders. Let's put in some placeholders for now. We could switch to u, but usually in these cases it's just easier to go back. Okay, so dx over x, that's du, and 1 over u squared. So this is u to the negative 2 du. All right, natural log of x is u, so that's a u squared in the bottom. The exponent, change the sign, moves it upstairs, so we have a u to the negative 2 upstairs. And the dx over x, that's the du. So now we have a power rule situation. Power rule situation, this is going to be limit. Let's see, add 1 to the exponent, divide by the new exponent, negative 1 youth. Negative 1 youth. So negative 1 over u. And then we're going to go back to our x's. So this is going to be negative 1 over natural log of x. And this then was from 2 to b. And we have limit. We can put the negative sign out in front if we want. We could, come on, go away. So negative 1 out in front, and then we have limit of 1 over natural log of b minus 1 over natural log of 2. We're taking that limit as b goes to infinity. This right here goes to 0. So natural log of b as b goes to infinity, looking like the bird wing, it's going up to infinity. Slowly, but it's still going to infinity. So that fraction must be going to 0. So therefore, this all becomes 1 over the natural log of 2. So that tells us that both converge. So therefore, both converge. So with an improper integral, when we have a positive decreasing continuous function, that number, if it converges, we get a finite real. We get a positive real. Sometimes we're going to want to use some notation to emphasize that this is a positive real. So if you get a number, you know it converges. Sometimes you're going to see this notation. This is a positive real. So the two-stroked R means all real numbers. That means element of, and if we put a plus up here, that's a positive real. If that's a positive real, that means that improper integral is finite. That also means the series is finite. The series converges. All right, so now we see kind of a new threshold. So if we use natural log of x as a sort of micro bumper of the denominator, if you just bumped it by 1 natural log, it wasn't enough. But if you bump it by 2 natural logs, that's enough to actually create convergence. The terms are going to go to 0 fast enough. Fast enough. Fast enough. And that's, there's no other function that grows really slowly that we tend to look at. Natural log is the natural choice as to increase something by just a little bit. K, ln k is going to be just a little bit more than k if you start looking at graphs and things. So that's it just gives us sort of a new insight. K natural log of k in the bottom, not enough. K natural log k squared, it's enough. All right, let's go ahead and take our 10-minute break. Take a 10.
When's test 3? 16th. April 16th.
April 16th. We'll be done with our taxes. Hopefully. Well, is tax day this year is tax day the 16th or the 15th? this year?
They bump it, what day is the 15th off?
Normally it's the 14th, right? And the 14th is Sunday,
So then
so
it's
it's
the
the 15th, right?
If it falls on the weekend, then it's the Monday
And that's
after.
the Monday after, which tells me what I'll be doing that weekend.
And that's okay, so the 16th?
Yeah.
Okay.
Oh, Monday the 15th is a holiday? Is that what you just said? What did you say?
Oh, no, it's a Tuesday. I'm just trying to get work schedule figured out.
Oh, gotcha.
Closest we gonna get 3 years. Really close.
Getting big raises. Okay, so let's take a look at this one. You all try number 26. So use the integral test. When we think about it, when we think about that one, the terms are going to 0. Divergence test is inconclusive. Everyone agree with that? K cubed in the bottom, k squared up top, that's going to go to 0. So go ahead and set up your integral test and see if you can decide whether it converges or diverges via integral test. Let me know if you're having trouble with the integration. Make sure you put your limit in there. Anytime we have an indefinite an improper integral, we need a limit. Must have a limit. Sure. Oh, yeah. Yeah. I mean, especially when we're in series, limit always means it's k goes to infinity. Yeah, totally fine. Totally fine to drop that off. The thing you don't want to drop off is the LIM. Yeah, you can drop off the subscript. Totally fine.
Yeah. No, it's just so we all
It should be fine. Oops. What form is that integrand in? What form?
It's in log.
Log form. Yep, log form. Everybody seeing that? Log form. What's the derivative of the denominator? 3x squared. So we're missing a 3, so we would have to do a little massaging. Put a 3 there and put a 1/3 maybe all the way out in front. Everybody see that? And once it's in log form, take it from there, write down your antiderivative. So when an integrand is in log form, we get natural log absolute denominator. Does that all look good? Then we plug in our upper limit. And we're going to get natural log of b cubed plus 5 minus natural log of the lower limit, natural log of 6. And what happens with that limit? Infinity. Therefore, converge or diverge? So therefore, diverge. Now, let's go back to the original summand and look at that and think about whether that's logical. And the answer is, yeah, that's logical. The essence of this summand is 1 over k. Right? The 5 is doing diddly in the bottom. If we imagine just sort of erasing the 5, doesn't this behave like 1 over k? Right? That's going to behave like 1 over k. So the nature of this summand is 1 over k. That's really what it's acting like. And we know that 1 over k diverges. So yeah, it's logical. Makes sense. Okay, now they're going to get funny on us. So we've seen that 1 over k ln k diverges, but 1 over k ln k squared converges. So now they're like, oh, well, let's try something in between. So this natural log of natural log, that's still bigger than 1, but it's going to grow a little bit slower than just natural log of k. It's going to grow a little bit slower. So now they're trying to figure out, we're just getting funny here.
Why are they so obsessed with this function?
Right? They want to know the threshold. How close can we get? Okay, so we're going to use the integral test here. So we're going to say the limit as b goes to infinity of integral 3 to b, and this is going to be dx divided by, if we switch over to x's, x ln x times ln of x. And what do you think we should let u be?
ln x.
No?
ln of x. So ln of x is not a bad guess because its derivative is present, but we want to let u be the most complex part of it that has a derivative that's present. So if we let u be the ln of x, look at what happens.
Oh, then it's the other, okay.
Then the whole denominator is going to be spoken for. So the derivative here is 1 over the inside. Okay, so the derivative of the outer ln is 1 over the inside.
Yep.
Times the derivative of the inside. The derivative of the inside is 1 over x, so we can put that. And then a dx. All right, so this,
CU.
right? All that right there is du. All right, let's see.
Makes this log more.
So we're going to get integral. We're going to use some placeholder limits because those limits, we don't have u limits. We don't want u limits. Okay, so dx over x ln x, that's all du. So don't we just have 1 over u du?
Yeah.
Is this really room to ln of x?
So that integrates to ln of u. Now we already know u is positive, so we don't really have to put absolute value if we don't want to, but we'll just leave it for now. Put some placeholder limits. Excuse me, placeholder, yeah, limits of integration, placeholder. So this is going to be limit of ln of x.
Throw another one in there. Let's see what happens.
Why not? So we have that. We can see where it's going, I think. So this is going to be the limit as b goes to infinity of ln, what's that? I'm getting sick of writing parentheses. That
Don't write
minus,
them. It's fine.
okay, and where does that limit go? Infinity. So therefore, diverge. So, I tried to slow it down a little bit, slowed it down too much. Crazy. Crazy talk. All right. Okay, so the next test is more like the geometric series test. Right? The geometric series thing's not really a test. You know, if you identify it as a geometric series, you find A, you find R, and if R is less than 1 in magnitude, it converges. We consider it a test, but it's much more of a, you know, a form, geometric series form. And the P-series is more like that. And the P-series, everyone loves the P-series. It's really easy. It parallels what we did with improper integration. So 1 over, when we're doing improper integration, 1 over x squared, converged. 1 over x cubed, converged. 1 over x diverged. So all the P-series is doing is looking at those cases where we have powers of x. If we're thinking of the improper integral, we're thinking powers of x. When we're thinking about the infinite series, we think of powers of k. But in our mind, we're thinking powers of x. We're thinking of that half pipe thing, or quarter pipe, going down to 0. And if that power is bigger than 1, converge. That's it. So P-series is like geometric series. You identify P, make a conclusion. Geometric series, we identified R and made a conclusion. If R was bigger than 1, for a geometric series, we had convergence. Here, for a geometric series, if R was less than 1, we had convergence. For a P-series, if P is bigger than 1, we have convergence. So, all of a sudden it feels like that dyslexia type of thing. Wait, which is which and why? Well, for a P-series, our focus is in the denominator. If P is bigger than 1, that means the denominator is growing fast, so the fractions are going to 0. With a geometric series, you're looking in the numerator. Right? With a geometric series, you have the series that has this arc form, a r to the k. That r is in the numerator. So numerator less than 1 converge, denominator bigger than 1 converge. So that's why they're different, but we have to keep those two straight. Those are the two that are super easy to start getting tangled with. Geometric series, less than 1 converge. P-series, bigger than 1 converge.
Never mind. It'll just confuse people. It was to do with it being a negative exponent, so you could do less than negative 1.
Stop. Do it. Negative exponents? No negative exponents. It's going to get way more confusing than it needs to be.
That's why I stopped.
Right, negative exponents are just bad.
What about imaginary exponents?
Stop. So this series right here, let's rewrite this first. Let's think about the divergence test for a moment. Is this going to convert? Are the terms going to 0 or not going to 0?
Going to 0?
Do we agree? Going to 0?
Pi is greater than
So E is smaller than pi, so we could rewrite it like this. We could rewrite it like that. And I'm just going to shorthand the notation on the summation symbol. Just put a 2. We know it's going to infinity. If it's not going to infinity, we definitely want to put an upper limit. So we have this. Now let's ask the question. Is pi minus e greater than 1? So this is really definitive. If it's bigger than 1, it converges. If it's less than or equal to 1, it diverges. Is pi minus e bigger than 1? Let's see. So this is approximately 3.14 minus 2.71.
No,
No what?
it's not bigger than 1.
Oh, okay, thank you.
Not zero.
So this is
Great
less
You got pi wrong.
than 1. Do we agree? Less than 1? So therefore,
Diverges.
diverges.
Oh no.
So, diverge. So this is parallel to all that stuff we did with the horizontal tails, the horizontal unbounded tail. The power on x is bigger than 1, converge. Power on x is less than or equal to 1, diverge. So it's not, like a test in the sense that the integral test, it's more of a form. You identify p, make a conclusion. So I should put a p up here just to emphasize. So p is that exponent. We need to get it in this form, 1 over k to the p. We want to put it in that form, 1 over k to the p. And then we can make our conclusion. Okay, so here we look, we see this stuff going on. Let's bring the 2 out in front. And we've already sort of talked about the fact that a multiplication by a constant has no bearing on convergence or divergence. So that 2 we can basically ignore. Now it's not in the form of a p-series yet. It's not in the form of a p-series until we have 1 over k to the p. Now it's in the form of a p-series. So we want to put it in the p-series form. We want to identify p. So in this case, p is equal to 3/2. We want to compare it to 1, and then we make a conclusion. Converge or diverge. So those are the steps. Put it in the p-series form, identify p, compare it to 1. Bigger than 1, converge, otherwise diverge. So make sure on your test that you do these 2 things. Make sure that you identify p, so I know you know what p is, and then compare it to 1 and make your conclusion. So those 2 things, identify p, compare it to 1. All right, you all do that one. Now think about it in your head also. Think about the nature of that summand and whether the answer you get makes sense based on what the nature of that is. Converge or diverge?
Diverge.
All right, so let's see. So here is the math. So intuitively, we should be thinking diverge. So the third root of 27 is 3. So we can pull that all the way out to the front. So we're going to just try to rewrite this so that it's in p-series form. So the fraction is going to be 2/3 on the k. So now we've rewritten it in the form of a p-series.
And why does it not converge because 2/3 less than 1?
That's right. 2/3 is less than 1. So for a p-series, 1 over x squared converges, 1 over x diverges. Under 1 diverges, bigger than 1 converges. So first we identify p. And then we compare it to 1, it's less than 1, therefore diverge. So if it's bigger than 1, we have converge. If it's less than 1, we have diverge.
Wait, 2/3, wait, what's the difference?
Those things.
So this one is bigger than 1, that one's less than 1. So for a p-series, whenever that p is bigger than 1, so like 1 over x squared, 1 over x cubed, 1 over x blah, 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 that'll converge, but if it's a fractional exponent, it's going to diverge. A proper fraction. Not 4/3. 4/3 would converge if the exponent was 4/3.
Or 3/2.
Or 3/2. Or 9/7, or
About
1,001
0.9 repeating over 1. Oh wait, I guess those
0.9 repeating is the same thing as 1, so then we would have divergence.
So if one, okay, so if it equals 1?
If it equals 1, there's divergence, because then we're in the harmonic series.
Okay.
So if the p-value is exactly 1, then it's a harmonic. So when you have a harmonic, you could say that it diverges by p-series, or you could say it diverges by integral test.
Okay.
So you can kind of go either way with it. So if p is equal to 1, it diverges, or if it's smaller than 1. So equal to 1 is that special case of the harmonic. Choose your test, determine whether the following series converge or diverge. Okay, that's all this chapter is about. Okay. So, first thing, we always think about limit of a sub k. That should at least cross our mind. So we glance at these three. That one, oh, definitely goes to 0, definitely goes to 0. That one, what's the limit of a sub k for that one? 1.
Square root.
So, if we take the limit of a sub k for this one, this is the limit of the square root. And now we've talked about the limit and how clever it is. It's very stealth. Like if we wanted to be really, really precise or anal, you could push the limit inside. We never write this step down, but that's what's happening. The square root function is continuous, so the square root can go in. If we wanted to get just so tedious, we could. Then this is the limit of the numerator over the limit of the denominator. We never write all these steps down, but so then we get infinity over infinity, and then we use L'Hopital's rule. Long story short, we get 1. K over k plus 1, the derivative of that is 1, the derivative of that is 1, the limit is 1. Okay? That is not equal to 0, therefore diverge. So the divergence test, if the limit of a sub k is not 0, must diverge. No other choice. Okay, now we look at this one. What's your intuition? Is that one going to converge or diverge? It's going to converge. It's going to act like 1 over k squared. Adding 9 and multiplying by 10 is not going to change the nature of the convergence of 1 over k squared. So that is now that's not a p-series the way it looks. Right? It's like a p-series, and once we get to the comparison tests, we could treat it in comparison to a p-series, but the way that sits, it's not a p-series. A p-series is 1 over k to the p. It's going to behave like a p-series, but it's not a p-series. So for this one, right now, we would have to use the integral test until we get to the comparison test. So let's see. So if we're going to do the integral test here, we're going to integrate. We're going to take the limit from 0 to b as b goes to infinity. 10 over that. And I want to put an x instead of a k. More palatable. All right. So the integral of this, let's factor out the 10. The 10 is in the numerator. And what are we gonna factor out of the denominator?
1/9.
I'm gonna factor out the 9.
Oh, yeah, 9.
I'm gonna factor out the 9, and then that's gonna put it in inverse tangent form. So then we're gonna have x over 3 squared plus 1. Now it's in arctan form. So we're pulling out that 9, just as a reminder, there's no 9 over here with the x's, so we can think of putting it at 9 over 9 as a coefficient. And then we're factoring out that 9 to right there. All right, now it's an arctan with reverse chain rule. Arctan with reverse chain rule. So we have 10/9 out in front. We have limit. That's going to be arctan of x over 3. So arctan x divided by 3, and then
Divided by the chain rule.
divided by the derivative of the inside here. What's the derivative of that?
1/3.
1/3. Dividing by a third means multiply by 3. So we're going to have that. This is evaluated on the interval 0 to b. So this is then going to be 30 over 9. Limit, as b goes to infinity.
30 over 9 or just 10 on 3? Easier, right?
Oh, yeah, good point. We could cancel the 3. Yeah, we'll yes, 100%. And that will be inverse tangent of b thirds minus inverse tangent of 0. So cancel out the 3, so that would be 10 thirds times, let's see, what's arctan of 0? 0. Arctangent of 0 is 0. And arctan of b over 3 as b goes to infinity. Pi over 2. So we know the arctan function. If we just look at the right-hand side of it, the arctan function looks like this. And it's got a horizontal asymptote at pi over 2. So as b goes to infinity, the inside of arctan is going to infinity, so the arctan values are going to pi over 2. So pi over 2 minus 0, so we end up with, yeah. So pi over 2, we end up with 5 pi over 2.
5 pi over 3.
5 pi over 3, thank you. So 5 pi over 3, and that's a finite number, that's a positive real, that's an element of the positive reals, therefore both converge. So since the improper integral converges, the series converges. All right, cool beans. And that, again, it reinforces what we knew was going to happen, right? 1 over x squared converges, 1 over k squared converges, we know. But the essence of this, the nature of this is 1 over k squared. Adding a constant, multiplying by a constant, that's insignificant. Okay, now we have this crazy looking thing. All right. Again, we suspect that it converges. Because the k squared is going to be the denominator. We're going to have a 9k squared. But what techniques? Anyone have an idea?
Integration by parts again?
Yes, parts or PFD? What did you say?
Partial fraction.
Partial fraction
You could also-
decomposition.
you could
So
also-
partial fraction decomp will allow us to break it apart and then hopefully integrate more easily. So let's see what happens. So if we take
Could do 2
this, so right now
integration by parts.
we have 2 linear factors in the denominator. When you have linear factors, your numerator is just going to be a constant. So this is what the form of our PFD will be. So if the denominator is factored, think PFD almost always. If they're factoring the denominator for us, let's see what happens. See what PFD will give us. So hopefully PFD is going to give us something nice. So we're going to have 3k plus 4 times A plus 3k plus 1.
Isn't this the case where you can use the convenient value
Yep.
thing? Okay.
Mm-hmm. So there's our PFD equation. So we could notice that there are two convenient values.
Wait, is this supposed to be 3K? No, what?
You see it?
Yeah.
Okay. So let's go ahead and pick some convenient value. Ooh, convenient. Not converge. Convenient values. So let's pick k equals, what's the convenient value for this one? Negative 4/3. So if we plug in negative 4/3 there, the 3's cancel, we get negative 4 plus 4, which is 0. So that's gone. So on the left side, we have 1. On the right side, that's gone. Plug in negative 4/3 right there. We get negative 4 plus 1, which is negative 3. And we've got our b value right away. That's going to be negative 1/3. Another convenient value, or the other convenient value, is negative 1/3. Negative 1/3 here causes this term to be 0. So negative 1/3 is convenient. If we look at the other term, plug in negative 1/3 right there, we get a negative 1. So we're going to get 1 equals 3a. So a will be 1/3. All right, interesting. We have one positive, one negative. At first, maybe we were thinking we could, break it apart and use the integral test, maybe. But now we're seeing that what kind of series is this? (3k plus 1 minus 1/3). What kind of series is
Oh,
this?
telescoping.
Telescoping. So when we have that subtraction piece in there, that is going to be a telescoping series. Now this one's going to be a little more complicated than some of the ones that we looked at because the difference in these denominators is 3. We saw that when the difference was 1, like we had a term in the front and a term in the back for S sub n that were preserved. If the difference was 2, we had a couple of terms. So might have to be a little more careful with this one. So with a telescoping series, we want to find S sub n. So we have a couple of things we could do. One thing we could do is factor out the 1/3 just to clean up the integrand a little bit, or the summand a little bit. If we factor out that 1/3, then that makes it just a little bit less fraction-y. So we've got that. All right, so with geometric and telescoping, we find S sub n and then take the limit. For geometric and telescoping. So S sub n is the sum of the first n terms. This starts at 1, so that's cool. Then we just go from 1 to n. Nice and simple. Plugging in a 1, we have 1 plugged in for the k, so we have a 4th minus, plugging in a 1 there, a 7th. So there's the first term. Second term. Plug it in, and I'm just going to focus on finding the infinite series S sub n. I'm focusing just on this. In the end, we would, if we really wanted the sum, we would have to multiply by the third. So let's just see if it converges first and foremost, and then we'll deal with what it converges to in a minute. So, okay, there's plugged in a k equals 1. Now we plug in a k equals 2, so we have 1/7. Oh, this one.
You just cancel that immediately.
Yeah, it's gonna be, I was thinking that we were going to have a bigger spread.
It's because it's
But-
a difference of 3, but you're
it-
multiplying by 3.
And it's because of the 3, yes, exactly. So
So
once,
if you factored out another third, you'd end up with 1/3 and
then
1 1/3.
Then we would see,
Ks.
yeah, that's right. Okay, so if we plug in a 2 there, 6, all right, so we get that. Yeah, so this is going to be kind of easier like the ones that we have seen. So now we're going to plug in a 3, we get a 10 there. Plug in a 3, we get 13 here. plus the dots. And now let's think about our k values and our term numbers. So this was k equals 1, and it's the term, the term, so k and the number match. So that's 1, this is 2, this is 3. If we want to go to the nth term, we need an n minus 1 and an n. That'll be the sum of the first n terms. So now we have to plug in n minus 1 to get the n minus first term. All right, so we have to do a little distribution here. So that's going to be 3n minus 3 plus 1, so 3n minus 2 minus n minus 1 here, that's 3n minus 3 plus 1. We're going to end up with 3n plus 1. And then the nth term, we just replace the k with an n, so we have 3n plus 1 minus 3n plus 4. All right. Move that over there. So any questions for finding S sub n? So that's the expanded form of S sub n, and then we can do some cancellation. And if we see all this cancellation here, the only term on the front that's left is the 1/4. If we go from right to left, first is canceling with second of prior. So first is canceling with second of prior, first is canceling with second of prior, somewhere in the middle. So the only terms that are preserved then are those. So it is not more complicated than the ones that we have seen. So now this is the partial sum, S sub n, for the series part of it. We still have the multiplication by 1/3 to keep in mind. So there's S sub n, and this tells us that S is going to equal 1/3 times the limit of this. And what's the limit of that as n goes to infinity? 1/4. So the sum of this series will be 1/12. So like the geometric series, we can actually find S. Most series we can't. So a good little refresher on telescoping.
And what would it have to be for it to be 3 terms separated?
So if this was just a k plus 1 and a k plus 4. So
Then the difference is 3, whereas we confused it on this one, now it's 3 times 3.
yeah. So because they put the 3 in there, they took the difference of 3 and reduced it. So it didn't really act like they were 3
But
apart.
if it was just k plus 1.
K plus 1 and k plus 4.
We're going to have 3 terms.
Then we're going to have 3 in the front and 3 in the back. If it's a k plus 1 and a k plus 3, we'd have 2 in the front, 2 in the back.
Conveniently, all 3 in the back, if you're going to infinity, will all just be something over n, which will all go to 0.
Just figure out the last one.
All right, let's go to estimating series. So depending on what your major is, you will take courses in numerical analysis. A lot of times out in nature you're getting these infinite series and you need to just sort of truncate them and you want to get good approximations. And so the idea is, how do we estimate series? And because we can't add an infinite number of terms, so we need to truncate them. So we've got this convergence series. S sub n is the sum of the first n terms. The remainder, by definition, is the sum of the series minus the partial sum, i.e. it's the tail. Right? It's a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, etc. It's the tail. Everyone okay with that? Can you visualize that? S is the sum of the series. S sub n is the sum of the first n terms. So if you subtract off the first n terms, you're left with the tail. Okay, so that's how we're going to define R sub n. So R sub n is going to be the tail for S sub n. And if we look at a visual here, so we can get a gauge on R sub n. R sub n is going to be less than the integral from n to infinity. Let's visualize this. So don't look there quite yet. Let's come down here. So if we draw our terms, build the rectangles to visualize, we can either have the visuals to the right or to the left of the curve. I'm going to draw them to the right here. So there's S sub n. That's S sub 1, S sub 2 is the first two, S sub 3, etc. There's S sub n. So the blue rectangles all added together, that's S sub n. R sub n is then the rest of the rectangles. So R sub n is going to be the beige rectangles out there. All right. So let's look down here. So let's do the other option. Instead of visualizing our rectangles to the left of our point, let's visualize them to the right of our point. Same blue rectangles, same beige rectangles. So we've got the same ones. There's 6, there's 6. Same exact ones, but everything's shifted over a little bit. And when you visualize them to the right, you're getting this overlap. Similarly, for the beige ones, we're going to get overlap. So what this tells us, in both cases, the beige is R sub n. The beige is R sub n no matter what. So R sub n, we're going to put it in the middle, and it's going to be less than the integral from n to infinity. The integral from n to infinity is grabbing all the way under this curve, right? And that R sub n is smaller, right? It's under the curve. So it's smaller than the integral from n to infinity. But if we look down here, there's the curve going through those points. Here, the beige overestimate the integral. So the beige are going to be bigger than the integral from n plus 1 to infinity. So we're visualizing the same rectangles. Up here, we get this integral. Down there, we get that integral. And that puts us in a situation where we have bounds for R sub n. So R sub n has to be in between there. Let's come back up here. So here is the infinite series right there. There's S sub n on the left, there's S sub n on the right. If we add the overestimate integral, that's going to give us an upper bound on the series. And if we add the underestimate integral, so there's the underestimate integral, is the one with n plus 1 to infinity. So underestimate plus S sub n, it's got to be just under the series. S sub n plus the overestimate, just a little bit more than the series. So that gives us gives us an interval that the series has to be in between. And so now you can imagine, we aren't going to do a lot with this, but if you get into a numerical analysis class, you start looking at these two integrals. Let's say you want the series accurate to 2 decimal places. Then you start figuring out what the n has to be, how many terms you have to go out in the series to get accuracy within 2 decimal places. We're not going to do that precision, but you can imagine looking at these two integrals and solving for n and giving you a sense of how accurate it is. At this point, we just want to sort of understand that if we've got this convergent series, you can come up with boundary values for the R sub n. And then in the real world, you'll figure out what that n has to be. Beyond the scope of this class. Okay, so next, let's go to one of the most famous functions in all of math. So the Riemann zeta function. Riemann zeta function is one of those functions that there is tons of research devoted to this function. So the Riemann zeta function, we used Greek letter z, zeta right there. The squiggle thing is a zeta. And this is what the Riemann zeta function looks like. It's this infinite series where we have k to the x. So zeta of x is the exponent there. So it's really just a p series when x is a real number. When x is a real number, it's just a p series. So bigger than 1 converge, less than or equal to 1 diverge. So that's the part, that's an important. For even values, so even positive integers, there is actually computational techniques that allow you to find the sum. So we had this series on the board earlier today, 1 over k squared. 1 plus a fourth plus a ninth plus a 16th. That actually converges to pi squared over 6. And there's a really cool technique to find this pi squared over 6 if you want to look it up. It's not too out of reach, but you could figure that out. Okay, so when x is real, it's just kind of p-series type stuff. What gets interesting, if you go look at like 3 blue, 1 brown, the Riemann zeta function, when you have complex exponents there, when that becomes complex, somehow the Riemann zeta function, when you have complex values there, somehow it can be used to predict the density of prime numbers in a given interval. When you look at that thing, there is nothing whatsoever, especially if you put a complex exponent, there is no reason whatsoever you would ever even dream of saying prime number. But the Riemann zeta function with complex exponents will predict the density, in other words, the number of primes between two big numbers. Shockingly accurate. So it begs the question, well, where are these prime numbers coming from? I see nothing to do with a prime number right there. So here is something that is so mind-blowing. Here we are going to look at two things. We're going to look at the Euler product. And the Euler product is this thing on the right. They use capital Pi for product. Here is the infinite series. So this is what we just defined. That's our infinite series. That's the Riemann zeta function. And what you can show with remarkably straightforward math is that this infinite sum is equal to this infinite product, where in the product you only use prime numbers. So the Riemann zeta function can be written as, there's the Riemann zeta function written out in its series form, its summation form. Here is the Euler product written out with all prime numbers, just over the primes. So 2, 3, 5, 7, etc. And that's where the prime numbers are coming from. If you look up online or if you go to the handouts, I've got it all worked out here with the Riemann zeta function. Oh no, I didn't actually put it on here because sometimes I give you an extra credit problem on the next test. Do you want an extra credit question on the next test? So the extra credit question, let's give you an extra credit on the next test. The one extra credit on the next test, show that the infinite sum is equal to the infinite product. If you look it up online, there's a million different videos of people doing it. It's one page, and you can understand every step of it. It's remarkably simple. So that'll be an extra credit on the next exam, to show that this infinite product is equal to this infinite sum. It's just algebra. Like literally algebra 2, shockingly. But that's where the prime numbers come from. So if you can prove that that equals that, then all of a sudden, when Riemann zeta function is creeping into the picture, primes don't seem that unrealistic to consider. But it's a really wild looking equality that this infinite product over primes is equal to that infinite sum. Not something that's obvious in the least. Lots of research dollars go into that function and trying to figure it out. Because one of the most famous unsolved problems has to do with prime numbers. Everyone know what twin primes are? Like 11 and 13 are twin primes. Twin primes are primes that have a difference of 2.
My A's in between the twin primes.
Right now. your age will not always be in between two twin primes. 19 and 17, twin primes. 29 and 31, twin primes. You can prove that there are an infinite number of primes, obviously, that's the easy proof, but it is still yet to be proven that there are an infinite number of twin primes. That is one of those, what do they call it, the millennial problems? You get $1 million if you prove it. Infinite number of twin primes.
The twin prime conjecture.
The twin prime conjecture. Yeah, you can make a lot of money if you can. So, interesting fact. So when I was in graduate school, I was in grad school in San Francisco, and my number theory professor told me about that. I was like, oh, $1 million to show that there's an infinite number of twin primes. So I started working on some things for that to try to get to the point, and it became important in the angle I was approaching it with to know how to determine if a number was prime or not. And to know whether a number is prime or not, you need to factor it. If the only factors are the p and 1, then you know it's prime. And so the one theorem that I ever had published had to do with this. And you all know you should know, it's not taught as much as it used to be. You know how to know when a number is divisible by 3, right? You add up the digits, and if that is a multiple of 3, the number is divisible by 3. Same for 9. If you add them up and it's a multiple of 9, it's divisible by 9. So in most number theory books you look at, they show you a test for 3, 9, 7, and 11, those 4 tests. And if you look at the proofs for those 4 tests, they're all done differently, all done totally randomly. And the one theorem I ever had published showed the connection between those 4 tests. And more importantly, it develops a test for every single prime number. It develops a numerical test, like using the digits of the number to figure out if it's prime or not. Add them up and do some things, and it will determine whether a number is prime or not. It'll determine whether it's divisible by whatever you want, divisible by any prime number. So if you can use that theorem to figure out the twin prime theorem, give me a cut. So it's helpful if you can tell whether a number is divisible by a prime. Okay, let's do one last interesting example, the dominoes. And so the idea here is, can you stack dominoes or bricks? And they're perfect. Dominoes actually have rounded edges, so maybe they're not perfect. But the idea is, can you stack them in a way, and if so, what's the minimum number, so that you can have the top domino or brick hanging over the base domino. So you put your first domino down, and then you start creating that little wave. Looks kind of like the natural log function. Can you stack them so that it will not fall over and have this domino totally overhanging the bottom? Think it's possible?
Probably. Yep.
It's possible. So then the question becomes, how many does it take? And so I'm going to imagine each domino is 2 units long. So there's first domino, second domino. You place the second domino just like that. Your overhang is going to be 1. If these things are machined perfectly, you can get a total. In practice, if you go do it with bricks, you're going to have a little less overhang. You still can do it with bricks and dominoes. But if we could do it perfectly, we would position the left edge of this top domino right at the center of mass of the lower domino. And then it would work. Then to put the third one on there, we would have to take and place, we would have to again do the same type of thing where we're going to look at center of mass. And if we take those 2 dominoes and place them right there, we are going to get, the center of mass is going to be right over here.
To be right on top of the edge, which is as far as you can go before it tips.
Before it tips. And so now we have a 1 plus a half as the overhang. Total overhang's 1 1/2. And then we do it again. We take those top 3 and we place it so that the center of mass is right there. We get 1 plus a half plus a third. Well, we get down to 5 dominoes, and the overhang is more than 2, and we started with dominoes of length 2. So if you do it perfectly, you can have an overhang with just 5. But what is this telling us? Do we recognize that sequence? Right? That's the harmonic series if we start adding those all together. So that means you can create as big a gap as you want. You can stack 100 of them, and if you put them at center of masses properly, you can create a massive overhang and it will be totally stable. Which is totally bizarre, right? Because it feels like it should topple over.
I need me some dominoes.
Just imagine.
Time to go buy dominoes. Time to go look in your
What if you had
bedroom from when you were a kid.
what if you had a domino buildings like that?
Yeah, it'd be cool.
Problem is, then
The precision that you need makes it very expensive.
also any outside force, it's perfectly balanced
Right.
at that, which means that any amount of wind or extra weight on one part will break it.
And let's be real, we're not gonna build it anymore because a plane could cause some problems.
Have you all seen the Tacoma Narrows Bridge video?
Yeah.
You seen it? Tacoma Narrows Bridge
With harmonics.
with the harmonics?
Yeah.
So they built the bridge and the frequency of the natural frequency of the bridge. They didn't take into consideration the frequency of the weather, and the whole thing explodes. If you've never seen that video, you've got to watch that video. Tacoma
Didn't
Narrows
it
Bridge.
amplify on itself over and over again?
Yeah,
Basically.
until it totally crazy. How about that bridge this morning? You guys hear about that?
No?
In Maryland, the container ship rammed into the bridge collapsed, and cars went flying into the ocean. And
Lesson learned, don't trust bridges.
right, if you're gonna go over a bridge, make sure there's no container ships down below.
Do it fast.
Just speed. That'd be a good excuse for speeding. I'm trying to get through the bridge as fast as possible, so
Yeah.
I don't want to bridge collapse on me.
I was living in California when that earthquake happened and the Bay Bridge partially collapsed. That was just crazy. Remember that one? Oh no, you were dead.
How much? When was that?
Oh, what year was that? The Bay Bridge and the upper part of the Bay Bridge collapsed and some of the cars fell into the lower
Early
part.
90s.
1772.
Yeah, was it early 90s or late 80s?
1772.
Can't
I
remember.
just
It was not in the 70s.
I'm probably like the only one in this group that
1772.
doesn't.
It was not in the 1700s. Okay, so anyway, infinite overhang is possible. Yeah, look up Tacoma Narrows, though. That one is cool.
Yeah.
All right, let's talk, in our last 4 minutes, we'll talk about this idea of a comparison test. So all of a sudden, the tests are coming fast and furious. So don't get behind on the homework, because there's going to be 10 tests, and they're coming fast now. So make sure you stay up on the homework, because you can manage all these tests, but you need to, but there's all of a sudden the ball's in the air. It just feels like we're juggling 5 instead of 3 all of a sudden. Okay, so let's get a sense of this comparison test thing. So the comparison test, which is usually, most books will say this is the direct comparison test. So we've got 2 series. Series A, so the A sub k series, that's the series we're analyzing. That's the series that's been thrown in your lap and you've been asked to figure out if it converges or diverges or else. So A sub k, A for analyze, that's the one you're analyzing. That's the one you want to know what happens to. Series B sub k is a series that we create. It's a series that we use because it's going to be a useful companion. So, if we choose series B sub k in a way that it converges, like 1 over k squared, 1 over k squared converges. So we pick a series that converges if we can show that the series that we're analyzing is always smaller, so term by term smaller. When we say series A is smaller than series B, we mean term by term. A sub 1 is less than B sub 1, A sub 2 is less than B sub 2. So each term is less than its companion term. Then A sub k series must converge. So if we pick a B sub k that we know converges, 1 over k squared, for example, and we can show that A sub k series is always less term by term, then the A sub k series must also converge.
Isn't the paragraph right below it saying that it doesn't always need to be less than, just,
Yeah, it needs to be less than eventually.
gotcha.
So as long as the tail is less, yeah, if we get into the nitty gritty, we could chop off the first 1,000, if maybe your series does some weird stuff, chop off. So what's important is that from some number on, the A sub k series is always less than the B sub k series, yeah. Similarly, again, we're analyzing the A sub k series, the B sub k series we are choosing. And so this is why the intuition piece is so important. We look at our series and we say, hey, it looks like it's going to behave like 1 over k. Or, hey, it looks like it's going to behave like 1 over k cubed. That informs us on what to pick for B sub k. So if we feel like the series converges, we want to pick a comparison series that converges. Or vice versa. If it feels like it's going to act like 1 over k, we want to pick a divergent series as our comparison series. So if we pick a B sub k series that diverges, like the harmonic, that's a classic example. So if we pick the B sub k series that diverges, the harmonic, and then we can show that all the A's are bigger than all the B's eventually, if we look out at the tail, then the A sub k series must also diverge. So to keep it straight in your head, the A sub k series we're analyzing, the B sub k series we're creating, we're conjuring it up. And then those two principles are what we're going to use for the comparisons. So we'll talk about the details of the comparison test on Thursday. Read ahead though, just to get an idea, because it can be a little complicated, but based on pretty simple ideas. Smaller than converging converges, bigger than diverging diverges.
By the equivalent in Boom Physics Lab.
Welcome back. You went somewhere, right?
Yeah,
In Bama. Roll Tide. Not Auburn? You're not from Alabama, though.
No, my parents, I grew up here, and my parents lived there.
My mom lived in Alabama for 30-something years. She worked for NASA. Yeah, it was cool. And yeah, she would take us, we'd go check out all the cool stuff there. It's so cheap.
Yeah.
There's a reason, though.
Yeah.
You're in Alabama.
Yeah, they just like bought a house out there straight out, and like now, like, they basically don't work. So
Yeah.
they're
How old
almost,
are they?
almost retired. Mom's like 45, and my dad's like 39.
And they're almost retired?
Basically,
Holy
my dad works like
smokes.
3 days a week.
Wow.
And my mom doesn't work.
That's great. And where in Bama are they?
Leeds, like a little bit outside of Birmingham.
Okay, Birmingham. Okay, my mom lived in Huntsville. Yeah. Oh, that's cool.
So
Yeah.
it's
Pain
nice.
in the ass to get there, though. It's not cheap.
Yeah. Well, we go to Atlanta, and then she
Oh,
picks us up.
Birmingham's close enough to Atlanta.
Yeah. And
Yeah.
it's like Leeds is like even further east,
So it's closer
yeah,
to
it's like
Atlanta.
hour 45 drive.
Okay, that's not too bad. In Huntsville, we would fly into Nashville and then drive for an hour and a half or 2 hours. It was flying into Huntsville proper always was like twice as expensive.
Yeah, I know flying into Birmingham's like 3-4 times as expensive as flying
Is
into
Atlanta?
Yeah.
Yeah. Oh well, welcome back.
Well, thank you. Nice to be back.
Yes.
You know, I had a job for 3 years.
Working at the grocery store for 3 years.
Yeah.
So you were still in high school when you started there.
Yes, like, and I was in high school until May 2023.
Okay. Oh, just last year.